During the mid-1960s, a pioneering group of Lockheed engineers set out to develop a revolutionary new weapon system for the US Army. The result was the AH-56 Cheyenne, an aircraft that combined the flexibility and maneuverability of a conventional helicopter with the speed and stability of a fixed-wing aircraft. The Cheyenne was one of the first aircraft to successfully harness the phenomenal control power of a rigid rotor, enabling pilots to easily conduct high-speed maneuvers during nap-of-the-earth flight. The system was compounded with a pair of stub wings and a powerful push-up prop that provided rapid acceleration to speeds in excess of 230 miles per hour. On board, an advanced, fully automated fire control system allowed the Cheyenne's two-man crew to simultaneously launch devastating attacks in every direction. Massive barrages of 30mm cannon fire, 40mm grenades, and even 2.75-inch rockets could all be delivered with pinpoint accuracy. The Cheyenne's fully integrated weapon system also featured extremely advanced range-finding and navigational aids that made it perfectly suited for a more hazardous mission: tank busting. With the push of a button, the gunner could lock a tank's coordinates into the fire control system. The pilot was then free to maneuver in and out of rolling terrain or to use the pusher prop to rapidly decelerate into a concealed firing position. At any time, the target could be reacquired almost instantly and destroyed with one of up to 36 TOW anti-tank missiles. As the roles and missions dispute evolved, another situation arose that would have a tremendous impact on the fate of the Cheyenne. In 1969, Bell Helicopter convinced the Army to buy 1,000 models of a new attack helicopter, the Huey Cobra, as an interim solution for the ongoing conflict in Vietnam. The Cobra was a modified version of the original Huey and was considerably less capable than the Cheyenne in many respects, most notably speed. But it was a simple, affordable, and reliable option that could pack quite a punch. In fact, as a result of the relative success of the Cobra in Vietnam, the Army apparently redefined its requirements for a new attack helicopter. High speed was no longer an issue, but survivability was. The new aircraft would only have to reach a top speed of roughly 185 miles per hour, but it would have to be equipped with 2 engines as opposed to the single engine that drove the Cheyenne. When Lockheed heard of the new requirements, it proposed a twin-engine, propellerless version of the Cheyenne. But there were other problems that were hampering further continuation of the program. For one thing, Lockheed's projected cost for each aircraft had risen from $1.5 million in 1966 to well over $3 million in 1971. The Cheyenne already appeared doomed when a final incident took place that ultimately sealed its fate. During a crucial meeting with government officials to determine if the program would continue to receive funding, a pair of TOW missiles were fired to demonstrate the system's phenomenal accuracy. Dozens of TOW firings had been conducted without a single glitch. But this time would be different. The first missile fired drove straight into the desert, missing its target completely. After the demonstration, Lockheed officials desperately tried to explain that the TOW missile had a failure rate as high as 10% and that they had never had a failure before. But it would do little to remedy the situation. On August the 9th, 1972, the Cheyenne development contract was officially terminated. While the missile failure alone did not kill the project, it is clear to many who worked on the Cheyenne that it provided the final excuse for those who opposed its ultimate success.
Records on and TM all set.
You run 12, item 36, taxi.
Nice lift off, breaking the record, record back on, going to air mode. Okay, right pedal turn.
Whenever you're set, if you would break the record for me, and it'll be run 17 for item 41, the takeoff and initial climb.
Roger that. Tower X2 ready for takeoff and transition to Eagle with chase.
X2, Glen Tower, wind 060 at 3, runway 9er, clear for takeoff.
Roger. Collective 60, coming to 56. Feet per minute, 140, 20 prop, and right turn chase to the west for the climb up to 5,500.
Okay, so we're coming up on 5,500. This will be run 21 for the level off. If you'd go ahead and break that record for me.
Right, record off, record on. Here's the level off. 22 prop.
We'll be looking to go out to like 32, 33 degrees on the prop, and we'll get going with the speed stuff.
Okay, engine torque looks good. Prop torque, record off, record on. Keeping a few more percent.
Okay.
245. 250. 251, that's pretty much level.
Break the record for me at some point. We'll do a little bit of a dive out to maybe like 260 or so.
Alright, record off, record on, lower the nose. There's 259. 260.
Yep.
262, and bringing the nose up. Bringing the prop back at the same time. Wow, that was nice. I can't thank you guys enough. Quite amazing here. This is why we all came to work at Sikorsky, is stuff like this. Thank you and appreciate it. And we'll see you when I get on the ground. Thanks.
Sounds good. A lot of fun.
Okay, there's the prop.
218, 219.
251, that's pretty much level. 260. 262.
Sikorsky Aircraft Corporation is deeply honored to be the recipient of the 2010 Robert J. Collier Award. We challenged the team to double the speed of a helicopter, but to retain all the attributes of a helicopter: handling qualities, maneuverability, ability to save lives.
This is not an incremental improvement. This is a real step change. It brings the helicopter into a totally new operational realm than it's ever been before.
It's a helicopter with better low speed, maneuvering and handling qualities, better hover performance, and seamlessly goes to airspeeds that no other helicopter could ever achieve before effectively.
The X2 performance was actually better than what we had predicted. When we hit the 250 knot milestone, we could have gone faster. We had more power to spare.
The rotor blade design, the fairing design, the integral propulsion, all those things combined to make an aircraft that has pretty remarkable performance, and it's still very efficient.
You're expecting to see the penalty paid in performance with either fuel flow or maneuvering performance, and that didn't happen.
Lower the nose.
The lift-to-drag ratio is the highest in the industry. It's the highest of any rotorcraft in the world, and that is a testament to the engineering that went into this aircraft.
We have new main rotor blades, which are highly efficient, very exotic, advanced shape, and all to the airfoils that reduce drag dramatically, both when you're hovering and especially in high-speed forward flight.
Here with this aircraft, again, the dual rigid coaxial rotor, that control input is proportionally and almost instantaneously transmitted to the control head. So I kind of relate its response to an F-16. You move the stick, you get an immediate response.
Safety was a consideration in the design of every part. And then when it was all put together, we had to take that design before the Model Development Safety Committee so that for every phase of envelope expansion we could convince them that what we were about to do had been properly prepared and that we had mitigated the risks to an acceptable level.
Part of our ground rule from day one is that aircraft only flew and continued to fly when everything was operational. All systems were go. And I think that was a big factor in orchestrating our safety approach.
Failure mode after failure mode were examined in the simulator. That was done so that Kevin could find out what the aircraft would do under those circumstances and practice recovering from it.
I'm a prior U.S. Army medevac pilot and officer and flew numerous combat missions in different theaters. And when I think back specifically to Desert Shield and Desert Storm and look at what I was flying and what I needed to do to respond to a wounded soldier or recover that wounded soldier to an evac hospital, I really am pretty proud of what potentially the X2 technology is going to bring just to that mission alone.
It wasn't all about product innovation, it was about process innovation as well. While we went 250 knots, we also asked the team to go fast. The result was an unprecedented 17 flights, 17 flight hours, and 250 knots.
We handpicked a very small team of new engineers, tech fellows, and folks in the middle of their career, combined them with an extremely interesting project, and then allowed their dedication and their enthusiasm to take over. This is why we become engineers, is to create something new that never existed before, that does things nothing else can do.
I think that every employee, 18,000 of us, carry the legacy of Igor Sikorsky, who was really one of aviation's true first and most innovative pioneers. It's an honor, but it's also our responsibility to continue that aviation spirit. We've done it by winning the 2002 Collier for the S92 helicopter. We've done it by winning the 2010 Collier for the X2 demonstrator. We're going to do it again by building the S97 Raider, and we're not done yet.
The
Bohaterem dzisiejszego odcinka Twardego Resetu będzie Sikorski. Śmigłowiec Sikorski S97, czyli najnowszy śmigłowiec Armii USA. Zbigniew Urbański, zapraszam. Po II wojnie światowej na ówczesnym polu walki coraz częściej wykorzystywano śmigłowce. W związku z tym pojawiła się potrzeba jak najszybszego dostarczania tego typu maszyn na potrzeby wojsk. W ten sposób powstało wiele konstrukcji używanych do dziś. Między innymi Bell OH-58, który w służbie armii USA jest od ponad 50 lat. Te wysłużone już maszyny wymagają jednak zastąpienia. A jednym z najciekawszych kandydatów jest zaprezentowany niedawno śmigłowiec rozpoznawczy Sikorski S97.
Ladies and gentlemen, the S97 Raider, our vision for the future of Army aviation.
Koncern Sikorski zaprezentował śmigłowiec S97 Raider w październiku 2014 roku. Jest to odpowiedź na sygnalizowaną przez armię USA potrzebę wymiany śmigłowca Bell OH-58. Zadaniem potencjalnego następcy tego śmigłowca będzie obserwacja i rozpoznanie. Nie jest więc to maszyna, która będzie przewozić setki kilogramów uzbrojenia, choć z czasem zapewne pojawią się mocniej uzbrojone wersje. Znacznie mocniejszym argumentem przekonującym Departament Obrony USA do wyboru S97 ma być jego prędkość. Śmigłowiec S97 Raider jest bowiem w stanie rozpędzić się do nawet około 440 km na godzinę. To blisko 2 razy więcej niż śmigłowce rozpoznawcze wykorzystywane do tej pory. Nieoficjalny rekord prędkości tej maszyny to 460 km na godzinę. Jak to możliwe, że śmigłowiec osiąga prędkość niewiele mniejszą od prędkości przelotowej współczesnych samolotów turbośmigłowych? To zasługa bardzo nietypowej konstrukcji S97. Składa się on z 2 współosiowych wirników nośnych, które wspomagane są przez śmigło pchające zamontowane z tyłu. Warto zwrócić też uwagę na obecność aż 2 wirników nośnych. Ich przeciwbieżny kierunek obrotu powoduje, że nie ma potrzeby stosowania w S97 klasycznego wirnika ogonowego. Efektem zastosowania 2 wirników ma być też obniżony hałas oraz wibracje konstrukcji. Oprócz tego S97 Raider ma oferować bardzo wysoką manewrowość. To wszystko przekłada się na mniejszą możliwość wykrycia i adaptacji na polu walki, a to cecha bardzo pożądana w przypadku śmigłowców obserwacyjno-rozpoznawczych. Bardzo mądrze zagospodarowano też kwestię miejsca dostępnego w środku. Oprócz 2-osobowej załogi we wnętrzu tego śmigłowca pomieścić się może nawet do 6 żołnierzy desantu. Nie ma bowiem wątpliwości, że na przestrzeni lat powstanie wiele różnych odmian S97, w tym desantowe, szturmowe, a być może także bezzałogowe. Sikorski S97 Raider wydaje się bardzo ciekawą propozycją dla armii USA. Nie jest jednak powiedziane, że to właśnie ta maszyna zostanie następcą Bella OH-58D. W kolejce do tortu wartego ponad 10 miliardów dolarów stoją także inni producenci. I żadnego z Polski. Niestety. To wszystko na dzisiaj w ciekawostkach Twardego Resetu. Do zobaczenia, trzymajcie się, cześć! Tym razem na tapetę wziąłem jedne z najdroższych i najbardziej zaawansowanych technologicznie sprzętów, czyli Parrot Zig-2. Czy ten sprzęt, telefon, który budzi skrajnie sprzeczne emocje, telefon, który jest koszmarnie drogi, czyli iPhone 6.
We have all seen situations where human life is in the balance. Situations in which a vertical flight aircraft could mean completing the mission or not, and in many cases, the difference between life and death. The ability to take off and land vertically has tremendous benefits, on the ocean or on land, where the most direct route is up and over obstacles. Helicopters' forward speed is limited by the rotation of their main rotor blades. Tilt rotors and vectored thrust aircraft also have drawbacks. Clearly, there is a need for an aircraft that can hover efficiently, but reaches high speeds. From this opportunity, X2 technology was born. X2 technology is a suite of technologies that when applied together allows efficient hover and acceleration to high speed with no in-flight transition. Rigid, counter-rotating blades, seamlessly integrated auxiliary propulsion, fly-by-wire with advanced flight controls, active vibration control. Sikorsky successfully developed and flew earlier approaches to a high-speed helicopter. Several technologies enabling high speed with efficient hover have advanced to the point that they can be bundled into a technology demonstrator aircraft. With conventional helicopters, the retreating main rotor blade stall limits total lift. As speed increases, a region develops where the blade is rotating away from the direction of travel and no lift can be generated. This region grows as the helicopter's speed grows. At 200 knots and beyond, the blade in this region is stalling. On the other side of the rotor, the tip is exceeding the speed of sound, resulting in a dramatic increase in vibration and power required. The X2, with counter-rotating blades, breaks these speed limits. Each rotor spins more slowly to keep the rotor tip subsonic at high airspeeds. The X2 enjoys the full lift potential of the upper and lower rotor's two advancing sides. The full use of this lift potential enables flight at 250 knots and also enables unmatched maneuverability. The X2 aircraft with two advancing side rotors has 1/3 the turn radius of a conventional helicopter, making it more responsive, lethal, and survivable on the battlefield. X2 technology aircraft will hover, land vertically, maneuver at low speeds, and accelerate seamlessly from hover to forward flight. In a high-speed configuration, one or more pusher props are part of an integrated auxiliary propulsion system to enable high speeds with no need to physically reconfigure the aircraft in flight. To demonstrate the viability of X2 technology, Sikorsky has built an X2 technology demonstrator. This aircraft is designed to demonstrate 250 knots cruise capability in a helicopter. Sikorsky's X2 technology demonstrator has made significant progress since its announcement in June 2005. In November 2005, a surrogate helicopter equipped with the new X2 technology fly-by-wire system made its first flight. In November 2006, ground test of the X2 technology demonstrator aircraft began with its LH-Tech T800 engine and drivetrain components. Major assembly of the demonstrator is now complete, and final test instrumentation installation is wrapping up. Ground testing is marching the aircraft through its required acceptance test procedures, ATPs, prior to clearance for first flight. Sikorsky has envisioned applications of its scalable X2 technology in a wide range of missions, such as combat search and rescue, armed escort, and missile site support. In an escort role, imagine a situation where an enemy aircraft is spotted. In this time-critical situation, an armed X2 technology aircraft can engage and destroy the enemy to allow the mission to continue successfully. In combat search and rescue operations, downed aircrew rely on the speed of the rescue helicopter to get them out of harm's way as soon as possible.
Bail out! Bail out! Bail out!
Travel Jelly 1-1 and 1-2.
Coordinates loaded. ETA to target, 22 minutes.
Roger.
In the same context, the CSAR aircrew rely on the speed and agility of their aircraft to get them to the survivors and back to safety.
Home plate. Survivors on board. ETA 30 minutes.
X2 technology can also play a vital role in protecting the nation's assets from attack. Speed and the ability to take off and land vertically are vital to enable access to locations not available to fixed-winged aircraft.
DRF scramble. Intrusion code 1 alert. Say 2223 en route. ETA 35 minutes.
Say 2223, have target in sight. Deploying TRF. Suspects get ahead.
Sikorsky has envisioned applications of its scalable X2 technology in a wide range of missions, such as search and rescue, medevac, armed escort, anti-submarine warfare, and anti-surface warfare. No other mission relies on the unique abilities of a vertical lift aircraft like search and rescue. Imagine an injured fisherman is 150 miles offshore. An X2 technology aircraft with its excellent low-speed handling and low downwash can rescue a person and bring them to treatment far sooner than conventional helicopters. The distress call comes in and the aircraft is launched. It arrives on the scene and hoists the injured fisherman into the aircraft and safely brings him to a land-based hospital. In another scenario, where enemy surface or subsurface forces threaten the battle group. In this situation, an armed X2 technology aircraft can engage and destroy the enemy to enable the battle group's mission to continue successfully. X2 technology-equipped aircraft are ideal for sea-based missions that require speed and maneuverability. Greater speed, flexibility, and agility translate directly into more rapid and efficient tactical mission area coverage. An X2 technology aircraft greatly improves the Navy's ability to detect, localize, and engage potential threats at increased range. Its adaptability and fit with current and future seaborne platforms make it a superior, mission-ready force multiplier. Sikorsky envisions X2 technology aircraft can support or perform insertion, attack, escort, and enhanced company operations missions.
Aircraft, clear to launch LSC signal, contact control.
In the sea-based insertion mission, the X2 technology unmanned system interfaces with an airborne command and control aircraft to identify, engage, and suppress a threat.
Shooters 1-1 and 1-2 inbound for your control.
We have 2 ZSU 23-4 and 18 troops in the vicinity of objective. Shooter 1-1 engaging. BDA as follows: 2 ZSUs destroyed, 15 KIA, 3 troops observed departing to the north.
With the zone secured, the Marines begin operations. X2 technology aircraft speed and maneuverability make it ideal for the escort mission. In this scenario, up-armored Humvees are external to their objective, but the CH-53 Kilo heavy lift helicopters.
99 aircraft, we have a leaker bearing 340 and 22 Angels 10.
Cali Bandit at 11 o'clock, engaging.
When an airborne threat emerges, the X2 technology armed escort aircraft swiftly intercepts, engages, and destroys it.
Bandit destroyed.
Upon reuniting, the X2 technology aircraft provides air cover, while Marines set up a security perimeter. Technology armed unmanned aircraft will also support sustained ground operations. Imagine that the platoon takes on small arms fire.
Taking small arms and RPG fire, 300 meters north of my position. Clear to engage, my mark, my control.
Coordinating with the airborne command and control station, the Marines on the ground call in air support.
Engaging. As follows, 15 KIA, 0 remaining.
Request immediate resupply.
Resupply mission en route, passing control.
With the area resecured, the Marines on the ground can be quickly resupplied from the sea. The ability to perform this mission in an unmanned mode will allow the Marine Corps to reduce the need to place troops in harm's way and provide greater flexibility to deploy Marines where they are needed most, where their skills are in greatest demand.
Mission complete.
The X2 technology stands ready to support every mission. Just imagine, what can X2 technology do for you?
Allez, s'il vous plaît, regardez-moi. Non.
The
speed and range of a fixed-wing aircraft and the operational flexibility of a helicopter. That's the promise of the long-awaited AW609 tilt rotor, and Augusta-Westland says it's now barely 3 years away from making the first deliveries. Augusta-Westland test pilots flew the 609 in from Dallas, where the program is based for now, ahead of a planned move to Philadelphia, where the production line will be located. They told AIN-TV about the difference a tilt rotor can make to an operator and what it's like to fly it.
I've been flying this aircraft for about 3.5 years, and it is a lot of fun. The advantage of a tilt rotor over a business airplane or a helicopter is the fact that we can do the entire mission of each of those aircraft. So, for instance, to come to this trade show, we actually left out of Dallas. We picked the aircraft, we climbed up to 23,000 feet. We flew at 250 knots true airspeed, and then we landed to a hover here at the convention center. We didn't have to use a runway, and yet we made it here in just a little bit more time than an airliner would have made it here. We can get out to the offshore oil well at twice the speed of a helicopter. We can go out much farther, so now with the deep water rigs getting farther and farther offshore, we can make it there without refueling. We can make it there over the weather. If there's bad weather, we'll just go on top of it. And we can make it there efficiently because we're taking advantage of the high altitude. And we can still come to a hover and land on the helipad on the oil rig. Or if you look at, for instance, a hospital, we could fly organs from an organ donor at one hospital, leave the helipad and fly to another helipad on another hospital where the recipient would be. No need to put them in an airplane and fly them, because we're going to fly just as high and just as fast as that airplane would have anyway, but we're going to completely eliminate the trip from the hospital to the airport and from the airport to the other hospital. Basically, our control system is very helicopter-like. So in the critical modes of flight, where you're taking off and landing, we are just a helicopter, and our flight controls act like a helicopter. However, on the left-hand collective grip, we have a nacelle controller, and it's controlled by your thumb. And you push it forward, nacelles go forward, rotated aft, nacelles come aft. And what you find is that in the lower speed ranges, the nacelle controller becomes your speed controller. So instead of pitching up like you would on a helicopter, you just rotate the nacelles aft and you'll slow down. And we tend to fly with a very level pitch attitude, and we use the nacelles to slow us down. Or on takeoff, we use the nacelles to begin the takeoff. So we're at a hover, we just rotate the nacelles forward to 75 degrees and away we go. And it climbs out very quickly because we get through effective translational lift so fast. When you're first taking off, your lift is being created by the rotors, not by the wing. And the wing is not going to become effective until you reach about 100 knots or so. So you can't rotate the nacelles as fast as you possibly could. You have to rotate them at a certain speed. And what we've done for that is we have preset nacelle angles. So when you hold the nacelle controller forward, the nacelles go to 75, and you're going to build up speed rapidly, and you're eventually going to get wing-borne lift. But they won't go past 75. And if they did, you could feasibly lose altitude, or even it wouldn't be safe. So it's very, very safe to have this 75-degree stop that we have on the aircraft.
Beyond this, engineers have also taken steps to protect against the danger of one engine failing.
We have a drive shaft that connects our two rotor systems. So if one engine were to fail, both rotor systems continue to operate completely as normal. And then our engines, we have electronic control on our engines, computer control, of course. So if one engine fails, the other engine automatically resets its limits to allow us to go into 30-second power, and that vastly increases the power of that one engine. And therefore, we can actually lose an engine at a hover, and at a lower gross weight, just slightly lower than our max gross weight, we would continue to hover. Even at our max gross weight, we would actually just land very softly. So, but there's nothing dramatic about having an engine failure.
At this year's Heli Expo show, the Italian manufacturer signed a key partnership with the Bristow Group, which will cooperate with the remaining development program for the 609 as a prelude to an anticipated order for the aircraft. It looks like something developed for a Hollywood blockbuster, but there's nothing science fiction about Finmeccanic's Project Zero tilt rotor demonstrator. The all-electric ducted fan design is the focus of a long-term technology demonstrator program for the Italian helicopter manufacturer. Among other partners in the program, the aerodynamic design was undertaken by Italian design house Bertone.
This is the world's first fully electric
converter plane, and also we developed something called the individual blade control, which is a unique control method that has never been done on any rotorcraft. In addition, the entire aircraft has made of carbon graphite construction, and there's no transmission, the direct drive, and powered by very high energy density lithium polymer rechargeable batteries.
Finmeccanic's Augusta-Westland division has yet to determine how or when the project may result in a defined aircraft platform, but the research work is already promising tangible benefits.
The advantage of the individual blade control is that we are able to control the blade pitch angle of individual blade individually. The advantages include now we can use it for primary control as well as using active control feedback, so we can vary the blade angle constantly as it goes around the azimuth to reduce vibration, to cancel external noise, to improve the aerodynamic efficiency, and to alleviate the gust response to give you a smoother and quieter flight. And all the technology we developed out of this, for example, this is all electric, no hydraulic, electromechanical actuator technology. Currently, we are borrowing that to put on other platforms. For example, a retractable landing gear on a helicopter are now electric powered.
The shape of the airframe may yet change after further as yet unscheduled flight testing. In theory, it could be operated as either a manned or unmanned aircraft.
Right now, we have successfully tested all the power system and lifted off the ground. And the next step is we are considering, could we one day go into a hybrid version of this? Besides just electric, we also been testing this with the model configuration to test the lift over drag and the flying characteristic. One day, we'll be able to maybe see a fully rechargeable electric vertical takeoff Project Zero flying in a decade from now.